Alright, hello, and welcome to the video for the February 2013 Circuit Cellar article for my programmable logic in practice. So I'm going to show you how to implement a peripheral. So this is going to be for the Zynq device, which is a combination of ARM and FPGA fabric. And this is going to be using the ZedBoard as an example, which is a very nice little development board for this device. Alright, so this is loosely based as well on the Xilinx HLS course, and one of their labs goes through setting up a peripheral, and it also goes through other details as well, but I'm just trying to show you a real quick edition of this. So the first thing I'm going to open is Xilinx Platform Studio. Let me get rid of this other one here. So Xilinx Platform Studio is what we use to make the project for the Zynq processor itself. So we go create new project, and we will decide where we want the project. So I'm gonna I'll make a new directory here. So let's just call this video, and then within video I'm gonna make an XPS directory, and I'll call it system, and we can just make sure it gets the right file name, XMP, system.xmp. Alright, and we'll leave all this other stuff blank for now. Okay, step one. Oops. So it pops up a little window here. Hopefully you can see everything in it. And I'm going to switch the board to be a ZedBoard from Avnet, and just make sure you have the right board revision. There's only the one right now, so that's easy. Go along. And here's where you can select any peripherals you want. So in this case, we actually don't need any of these peripherals, so we're just going to select all of them and just hit remove. Because we're using nothing of these. And I believe that's all we need, so we don't even have DDR or anything peripheral set up. So we hit finish. Alright. So while this is going, I'm going to switch back to the Xilinx XL high-level synthesis tools. And in this, I'm going to make the project that will become my AES core. So here we hit create new project, and again we figure out what that directory was. So in video, I'm going to make another subfolder HLS, and I'll call this Zynq AES video, or just Zynq AES. And I'll make a new file here, and this is going to be a C++ file. You could use C if you want. In this case, it doesn't really matter. I tend to just use C++. The main difference is when you go to use specific bit lengths of integers. There's two different formats. I won't put a test bench on right now. Again, doing the test benches is a good idea, and it's quite straightforward. For the videos, I'm really trying to show you some specific features and speed it up. That's why I skip them. So we're going to select the ZedBoard as the device, which makes sure we get the right device here. And hit OK. Hit finish. Alright, so we just have a blank file now. So what we need to do is to actually get some AES source. And I'm just going to copy an example AES implementation that I have. Let me just find this. So what the AES implementation I'm going to use is just this really dumb, kind of straightforward AES. And if you Google around, this will be, for example, one of the versions. I was using this in some other work, this Chip Whisperer, so this is done as a final project. Here they were using it on an AVR. But it's very, very straightforward, and we'll see how this, as a very first type of implementation, how well it works. So I'll go ahead and copy the AES source in here. And we'll immediately see a whole bunch of errors are popping up. That's not good, but that's okay. There's stuff to be done. In particular, we have this byte type, so what we need to do is just type def that. And I'm just opening other files here. So I need to go type def uint8 as byte, and uint8 isn't actually a type yet because I haven't included anything. So I'm just going to include the standard, is it AP int or AP int.h. So there we go. So this should have the, if I'm not mistaken, the uint8 type in there. We'll see if that goes away in a second. You may need to include the stand int. I thought it automatically, there we go. Okay, it doesn't automatically include it. So at this point, we still don't have the top function was called AES. So in this case, what's the top function called? Oh, AES. So we need to remake this to have the expected interface for our system. So what the expected interface is going to be is I'm just going to use this really simple idea where I have 128-bit wide integers that get passed, or pointers to integers. Obviously, you could also have stuff like FIFO interfaces or memory-based interfaces. This, to me, seems like the most straightforward. So what this means is that you're going to need to define that 128-bit integer. So we go ahead and add to AES. So remember, this is what we had before. And I'm actually just going to call this old. I'm going to make a new main function here, void AES, AP uint 128. And this is going to be the input text. AP uint 128, the key encryption key, AP uint 128, and the output text. All right. So initially, all I'm going to do is I'm going to make this really easy, and I'm just going to assign that the out text is equal to input text, and maybe let's add 1. So all we're going to do is take the input text, add 1 to it, and write it to the output text. So we can use that to validate if our system worked or not. And I'm going to run synthesis just as a first test to see if this works. And again, it comes up with some sort of error, so you can go ahead and see this. All that's happened is I don't have all of these functions declared. So I'm just going to simply cheat here and move this to the bottom. Try again. So this is just checking initially our file synthesizes. And we just wait for it to complete. All right, so something happened. It doesn't have an interface that we could actually use yet, and it's not even doing anything. If you remember, it just added 1. So first I'm going to get the adding 1 to work with the processor, and then I'm going to push in all of this AES code. So what we want to do is the AES, these 3 ports, we want to put directives on them, and we're going to specify the interface as being, what do I want here? Bus, I believe. Let me just double check. Oh, maybe it's not. Sorry, not interface I'm using. I'm actually going to use the resource. And there we go. So this lets me specify a core to connect it to, and I'm going to use this AXI for Light S core. And under the metadata, I'm going to go -bus bundle, so bundle together all of these, AES-IO, and I'm just making up that AES-IO. So there we go. We get this one here, and I'm just going to copy it for the other 3. So the key and the output text. So that's going to use this this AXI 4 core, and I also want to be able to get the return value. So if you just put variable equals return into that as well, this will put everything I need into that AXI 4 core. Alright, so let's try synthesis again. So hopefully this synthesizes a core that we can now use in our system. And I have the ZedBoard plugged in here, and we're going to use the serial port to connect it. So we'll play with that after. Alright, so that's done. Now I use this solution export RTL. Under export RTL, we go P core for EDK, and just hit OK. So that does some stuff. And if you were to look here in the Zynq AES folder, solution 1, we have this implementation directory with the P core stuff in it. So what I'm going to have to do now is this directory here, that P cores directory, I'm going to tell Xilinx Platform Studio that I want it to check out that directory. So we have to set that up as a user repository, and basically what you do is you put it here, and it has to be that P cores directory. Let's see if it picked it up. No, it didn't. So it's kind of annoying, this interface to it, because if it doesn't like the directory, it won't tell you unless you insert it through this interface. So we had HLS, Zynq, solution 1, implementation, P cores. Oops. So it just gave me an error and said that was incorrect, and I guess I want to be one above P cores. So maybe this XPS directory. Wait, no, HLS, solution 1, implementation. And then inside of implementation, we have P cores. Nope, keep trying. So this is what I mean, it would be nicer if it would just let you insert it directly. Okay, so final test, when you go to do this, use solution 1, not the implementation. You just click on solution 1 and set that as your user repository. I don't know why it has to be so specific about where it searches, and when you hit OK, it seems to take a while. Eventually it should search, and we'll come up with, there we go, so in the user repository, this AES top module. So I'm just going to go ahead and say we add that instance, and I'm pretty sure all the defaults are fine here. And there's only the one processing system. Okay. So, and you can look at all this stuff. Again, I'm not changing a lot of defaults here. There is more details in that Xilinx high-level synthesis lab that talks about doing the different options here. And you can go ahead and go to the addresses, and we'll confirm, for example, AES top is being mapped somewhere. We have bus interface, and that size is fine. 64K. You could actually make it smaller. It doesn't really matter for my system here. And let's go ahead and save project. Generate bitstream. Oops. Before I did that, actually, what I should do is export it to the to SDK, because that'll take a while. So I'll export and launch SDK is what I'll hit. And so this will generate the files required for the software development as well, and then open the SDK. So this step takes quite a while, so I'll just pause the video here. Alright, so almost done. We're just going through the bit generation and DRC check. So now it should export the design for SDK. So in the meantime, we can go ahead and look back at our AES code here while we wait for the SDK stuff to open. Oh. So it just opened here. And it'll ask you for a workspace, so wherever you want to save it. I'm going to put it back here. With everything else, so I've just put everything together. And once it opens, it should have the hardware file here. All right, so it's generated this. It's generated a platform. What we need to do now is generate a new project. Oops. So I'll go new application support. And I'm just going to make a standalone project here. That's easiest, and it's going to create a new board support project. Board support package, sorry. If you want, you can do that first. So you can either do it in 2 steps or in 1. For example, I can create the board support package, select which of the CPUs, and do that. Oops. And we're not going to use any drivers here, basically. It's just all standalone stuff. This is, a super easy example. All right. So there is a lot of resources for the ZedBoard in particular in terms of examples. So I'm really not trying to duplicate all that. I'm just trying to show you the requirements for the high-level synthesis stuff I talked about in my article. So we have to wait for this to finish, and then we can create a new project. Application project here. And what am I going to call this? I'm going to call this Hello AES, maybe, test. And here's where we have the option to just use that existing board support project, again, standalone. And it gives you some templates to do different ideas. So peripheral test, memory test. I'm going to use this hello world example. So it just says hello world in C. And builds it up here. So you can go ahead and look at that project. So there we go. So the first thing I'm going to actually do is I'm going to make a small change to this program that'll help us in debugging, and I'm just going to print the time that we compiled it like this. So time just gets defined somewhere and compiles OK. And we also want, at this point I'm going to change the linker script. So if you right click here, and it's actually off screen, there's an option to generate linker script, so you can't see it. But when you click this, it opens up this window here that helps you generate the linker script. And I'm going to change everything to internal RAM because this is a tiny program, and this internal RAM is more than big enough. I'm also going to change, the heap and stack. I might need it later, and we can check when we compile. So I'll change them all both to 2K, and it'll ask about overwriting the linker script, which is fine. All right, so now I connect the ZedBoard, power it on. I have it all plugged in here, so that's why I didn't have to do anything. And under Xilinx tools, there's an option to program the FPGA. So you hope that works. And I'm going to connect the COM port here. So I have a separate, oops, waiting for port. And I don't actually have the COM port connected, so let me grab another cable. Plug that in. Okay, so we now have COM69 coming up, and I have it at 115/200 baud rate. So finally what I need to do is I'll need to download the program to the device. So we'll create a new one here. So this is going to be the hello test ELF file, and it'll reset the processor, verify it. So here's where you can actually connect the USB standard I/O to the console. I'm not going to bother with that because I have another one running. So I'll just hit run and see what happens. So it gives you a thing saying launching here, so you just kind of wait. Until it's done. There we go, hello world. So we've not done a whole lot, we've just set up the example hello world application. The next thing I want to do is pull in drivers for that peripheral. So I'm going to add some source code here, and I'm going to say somewhere there's an import. Oh, there it is, import. And general file system. So I'm going to go ahead and browse to, again with the crazy friggin' file selection dialogues. I don't know why they don't use Windows 1, but anyway, it's an aside. So in this Solution 1 implementation, it gives you these drivers, which is what we want here. So I believe it's these 3 files we're going to need. And I'm just going to double check. It's not inside the P cores, is it? Oh, maybe it is actually. So it does a lot of stuff for you. Like as you saw, there was referenced ones that worked in Linux even. So let's go ahead and look at these. So it generates these files. So this is the one we want actually. So it's just doing read and writes for you. So I want to add these 3 files to the project. And I'm just going to say, okay, add these into the source folder. So it's copying them all. If you want, you can create links, and then actually when they get updated, these will automatically update. With this way, I would need to copy them over, which I'm just going to use copying for now because I don't want them to get screwed up. So it was able to compile them even. All right, so that's simple enough. What do we need to do? Well, you'll want to look at this AES .h file. So we're gonna, obviously the first thing we're gonna call is this initialize function, and it takes two pointers, so we need to make those. Well, the first thing we actually need to do is include that xaes.h file. Oops, and print gets defined somewhere else. So we comment that out. All right, so now we make xaes, I'm just going to call it AES, AES config. This is different. And this will initialize the system. We have our two variables, and I'll need to set up those variables. I'm just going to put all the calls in first. Like so. So all this is doing is initializing it, and we actually need to set up in this AES config. We're not using the device ID, but we are going to be using the base address. So what is that, and where do we find it? So this is important. The base address, if you remember, way back in the system, we had written what the base address was, but it's also defined somewhere here, platform config. Basically, there will be a definition of it, and I'm just going to copy it from my previous file. Oops, didn't like that. Oh, AES test. I renamed the module. I renamed the module AES. So where it's defined, just so you know, it's in this xparameters.h file. So if you didn't know what that name was, you would have had to go find in the board support package. I believe it's, oh, not here, sorry. The board support package, it's somewhere within here. So I believe there's this xparameters.h. Yeah, okay, that's where we are. So you can look through. So this has the base addresses for the different peripherals. All right, back to this. Get rid of that, there we go. It's looking better. Okay, so we needed to set up the, we need to tell it the base address here. And all I'm going to do now is I'm actually going to write to the input and read from it. So we have this set input and get output text. So I'm going to need that. And what you pass to it is the instance and the data. And the instance is this type here. And you can see it's just word 0, word 1, word 2. I'm just copy paste here to save time. So I'm just going to write a bunch of stuff to it. Like so. And then I can just call this function. And these are the functions that have been auto-generated for me. So you can improve them and make them more reasonable. Like you may just have a encrypt function instead of all this crazy stuff. So. Oops, input undeclared. There we go. And I then need to get the output. So the output is in a similar way, just like this. So get output data, and it sends it to a new variable. Now, before we do this, what did it like? Oops, that was the wrong one. It's just auto-generated a prefix here, which changed. So I don't use the output variable, which is fine right now. I also have to run this XAES, and these are just auto-generated functions here. There's a start function and an is done. So these are basically checking the HLS, start, done, ready lines. But anyway, I'm just going to say, okay, start processing that peripheral. And again, you start to see why you might want to make your own function where you just sort of rip out these low-level ones. And you can look if you're interested. So inside the XAES, you can see, for example, how we're just using the write register functions with an offset. So you wouldn't have to use this data word 0. You could just have a pointer and copy it all in, which may be easier, but I'm just trying to show you the default sort of functions it gives you. And I'm just going to, oops, what happened there? So while we're not done, we just go in a loop. Like this. All right, so this took some input in, put it through the AES block, and did some output. To print the data, I'm going to use some functions that print 32-bit variables. I'm just going to copy and paste them in here to save time. So you could also pull in printf and stuff. You have to be careful of memory usage and remember how much you put away in your linker script. So then I'm going to use these functions, and we're going to go ahead and print the input and the output to the block. So these print 32 hex just print one of the words. And it gives me some error. Oops. There we go. So yeah, so it's automatically compiling everything. And we can go ahead and download that. So what we see is that it has in fact incremented. We put in this, 128-bit number, which ended in beef hex, and it incremented that f by 1 and rolled this over to BEF0. So there we go. We just implemented a complete peripheral and got it to work with the software. Now that's not all I wanted to do. I wanted to implement AES. So let's keep working here. And now let's implement AES. So I'm just going to delete all this stuff here. And we're going to see if we can somehow marry these two systems. And I'm not going to return state. So before we passed it in a return value, so we're going to have to make a few changes. The first thing I'm going to look at doing is converting these 128 bits into variables somehow. So we have this integer. So I give some of the loops names. So for 16 I++. So for each of the bytes on the input, the state value is going to be, I've got to, get from the input, dereference it, and I'm going to select a range of bits. And the first 8 bits are going to map to byte 0. The next 8 bits will map to byte 1, etc., etc. So because of this, I'll use this format here. And that should be good. So we're mapping just 8 bits at a time over. And I am going to change the name of the global variable. From key to state key to reflect that it has some global significance. I'm just going to change it everywhere that it appears. Of course, you just find and release and replace, but in this case, it's all in this one function, so it's not really a big deal. Go. Okay, so that's everywhere that dealt with the key. Oops. And I just have to change that name there. Okay, so there shouldn't be any more errors there. So we have an input loop that's mapping both the key and the input data into the other format. And then we go through the encryption systems. And now at the output, before we used a return, we don't have that anymore. We just return a void. So I'm going to have an output loop. And I'm going to generate a temporary variable. Again, these things will get optimized away. So think like a C compiler where you can, you want to code for clarity. And you can make lots of duplicate variables, duplicate copies of variables. It doesn't mean they'll actually get implemented. It just means you can use them in the code. So again, I'm going to map onto the output variable 8 bits at a time. There we go. So this will map the data. And finally, set the output data as such. All right, easy. So we run the synthesis and then we export the design. So then this is now implementing the actual AES. And it's worth noting that this is sort of a very, very basic implementation of AES. There is some improvements you can make when you implement stuff in hardware. So it's giving me some sort of error here about, oh yeah, inline assembly. This code originally had some inline assembly for keeping constant time. So we don't, obviously that doesn't make sense. So we need to delete that. And can just go through while it's doing that to make sure there's nothing else crazy. One thing we're going to see is, for example, we have this lookup table here. This lookup table is used, this SBox, where's it? Where's a good example? So here we have this loop going through 16 times. It's going to be unable to unroll that loop because the SBox will be mapped to just one memory. And we can see this here. We're using a few memories for different things for storing these global variables, basically. So we have this SBox variable, we have the state and state key. If you want, you can switch to the analysis tab, get a bit more insight into these things. So you can see that the BRAMs are being used outside of, or the two sub-functions it's calling here. Switch to resources, memories, and we can see, okay, well, state key is taking a whole BRAM. SBox is taking a whole BRAM. This archon variable, which seems crazy, it's in a BRAM. But again, this is all the default stuff here, is showing you what it's doing. And remember, I've done almost no work at this point. So I'm just going to test this as working first. We export it. So the next process is long-winded. It's exported for EDK or the Platform Studio, same thing. Here I've got to go rescan user repositories, pick up those changes. I'll re-implement it. I'll export this once again to SDK. In SDK, I'll then rebuild the application and download it again. So we will say generate bitstream. So once again, I'll pause the recording because this process will take a while and isn't extraordinarily interesting to watch. All right, so we've finished generating the bitstream. We've updated everything, and we're going to now run the application. So this is with the AES core on the device, and we get the same result. And this is because I forgot to program the FPGA. Obviously, the bitstream changed, so that's critical. All right, so now the peripheral itself has been updated. So we go ahead and run it again. And we get the hello world. We don't get anything else. So sometimes just gonna try running it again to make sure. So it seems like the processor crashed here. I should have checked the. Really shouldn't have changed anything. But I'm just gonna power cycle the board here. Basically, I should have checked the size of the memory if I needed to increase that linker script. So this might have crashed the SDK. So I'm just gonna pause to restart it because it takes a while to restart this thing. Okay, so I restarted SDK, had to unplug the whole board and stuff. I don't know what happened, but anyway, so we can, it's downloading now. And what we should see, once the download finishes, hello world, some input and some output. So is this valid? Well, we have a problem here. We actually didn't set the key in this initial example. If you remember, I didn't have a key in this one because I was doing the adding. So every time we run this, we actually might get different outputs here, and we have no way to really validate. So I'm gonna make a new one, XAES key. I think that'll be what it's called. Yep. Okay. And I don't know, I'm just gonna make it all 2s. 1, 2, 3. Well, I'll throw in a few other things just to make it non-symmetrical so that no one thinks I'm cheating here. There we go. And I need to set key. All right, so I set the key, I set the input data. And we'll go ahead and run it. So that was the old run, and we get something different. Obviously, you expect this to be the same. We ran it multiple times if the encryption was working, which it is. And how I'm going to demonstrate it's working is there's a few of these AES test things. So these just do AES in your browser. If I were smart, I would have used one of these known keys, but I'm just going to copy it in here. And I need to make sure I get the order right, because 222 is word 3, which maps to the leftmost side here. So again, this was just a bunch of random crap. Is this right? So there's some issue, I think what I've done is I might have printed this in the wrong order. I'm just comparing to the, so word 3 is the key. Just make sure it actually, oh, so I've transposed the key. Let's try this again here. Where the key, so the key goes in the top one, plain text here. And it's telling me I expect to get this out of the encryption block. And here we go. Oh, yes, that worked. So there we go. We've implemented an AES peripheral for the Zynq hardcore ARM processor. I didn't touch Verilog at all. So that's amazing that you can do that in high-level synthesis. Now, one thing you might say is, well, that actually wasn't that good of performance. If I go here, it's taking 1400 clock cycles. So now I won't show you the full version working. You can download it from the web, but there's a number of things we can do if you want to increase the performance. So the first thing we're going to do is we can request that it pipeline it. So I'm going to go pragma HLS pipeline, and I'm also going to inline all those little functions, and I'm going to tell it to recurse down, so inline everything. And that's only going to go so far, because there's this issue I mentioned before where stuff like the state, this is implemented as a block RAM, but it can do, like, for example, this point here, it could be doing multiple shifts at one point. This is just remapping a bunch of states here. So when it's in block RAMs, it can't really unroll that very much. So we're going to tell it to store the state, instead of in block RAMs, just in individual registers. And I do this with a pragma array partition variable equals state. And I'm going to say do it completely one dimension. If you don't want to type all this, by the way, you can, of course, just click on stuff and add directives. Maybe I should have showed you that, but so, for example, where is the state variable? This variable here. So you can just say insert directive, but it doesn't like it because I just changed the file. So, and that might give us a little better performance. Actually, so this is cool. Just by doing that pipelining and inlining, it's now only taking 100 cycles to do the encryption. The area usage has gone up quite a bit, and because it's switched from block RAMs to LUTs. So it may have already actually done some of this. I believe it probably broke out some of these variables, so I might not even need to specify it. Anyway, but I will, and we'll see if that changes. So we had 100 cycles before. Can we get better? What's going to be the limiting factor in the end is this S-box. So this S-box is implemented as a single lookup table, but we need a bunch of them at once. We want 16 of them at once. So what you can actually do to improve this more is implement a bunch of S-box tables. I don't know of a way to force it to implement a bunch of ROMs. I didn't easily find one. And what I'm going to do is I'm just going to make a macro, and you'll see why in a second here. So now I have this S-box access macro, and this S-box access macro, I'm going to, oops, so it's done the previous one. So we didn't gain anything. It had already done the partitioning for us just by using the pipeline and the inlining. So what this macro is going to do is S-boxes, it's going to let me define multiple S boxes. And to do so, I'm just going to copy and paste here. I don't want you to watch me type all this crap. I'm going to define a new variable that's basically what you expect. So 20 copies of the SBox one. And rather than having this here, I'm going to go ahead and call this SBox data. And the final thing I have to do is I no longer have that SBox variable, which I referenced somewhere else here. So it would actually give me an error. Or it should. I don't know why it's not. But I digress. SBox access, and I'm just going to do these through macros as well. So why I've done a macro is that obviously this makes it pretty easy that if you decide, you know, oh, I want to use just one SBox because that takes up less block RAM, then you can do that. You just have to change the macro in the one spot, and you ignore the SBox number that I'm asking it to look up. Okay, so now we can run synthesize, and this will tell us the loop count, which should be way down. It should be at like 5 now. So as I mentioned, there is improvements you can do. So this whole SBox thing, you can actually replace, instead of using just a ROM, there's hardware implementations that are more efficient than just a lookup table, I believe. I haven't even bothered with that here. I'm trying to show you basically a generic algorithm, taking it from C code to a high-level synthesis design. Blah, blah, blah. And it's giving you some message. For example, the state key will not be exposed. You might want to do these as static. So there's certain things that aren't necessarily required, but will improve performance a bit, or will tell it a bit. So we're down to 8 cycles in the interval. There's more latency, so this means that it takes a bit to get going, but once it's going every 8 cycles, it could generate new. And I believe, I don't know if it's the Archon. So I'm also going to define these as const. Anyway, but you can go through, you can download the version on the website has 5 cycles to access the AES data, so it's quite fast. Well, I hope this was useful. It's a bit long, but I've been trying to slam through how we can use high-level synthesis to add custom peripherals to, in this case, the Zynq hardcore, but you can use this with the softcore processors as well. It's the same type of idea, and it even generates a bit of code to do the access for you. As always, there's more details, programmable logic in practice.com, or the Circuit Cellar article, February 2014 edition.